Welcome to today's Explainer, Rookie Detectives. I'm your lead investigator, and man, are we heading straight into the heart of Grade 7 mathematics today. Our mission? Well, we need to learn exactly how to verify mathematical claims using rock-solid evidence. No guessing here, folks. We're going to use tables, graphs, and equations to uncover the real truth about proportional relationships. So, are you ready to crack the case?
Here's our roadmap for today. First up, what are proportional relationships? Then, 2. Tracking tables for evidence. 3. The graphing test. 4. Equations as hard proof. 5. Comparing competing claims. And finally, number 6, the final verdict. Okay, let's dive into this right out of the gate. We've got a suspect claim on our hands. Someone is insisting that a taxi ride with a $4 base fare plus a $2 per mile charge is a perfectly proportional relationship. But is that actually true? Well, let's get to work and find out. By the end of our explainer today, you're going to have the exact analytical tools you need to put this real-world pricing claim on trial and prove it one way or the other.
What are proportional relationships? Before we interrogate our suspects, we kind of need to understand the fundamental laws of our mathematical universe, right? And it all comes down to this definition, the constant of proportionality. Mathematicians just call this K. This is a constant number that every single measure in your first quantity, your input, must be multiplied by to give you the corresponding measure in your second quantity, the output. This constant multiplier, K, is literally the anchor of our whole investigation. For a relationship to be truly proportional, this multiplier cannot change. It has to remain absolutely identical across every single data point you look at.
And that brings us to our two strict laws. For a suspect relationship to be proven innocent, which means it is proportional, it has to pass both of these rules with zero exceptions. Law number 1, it needs a constant ratio. That means the output y divided by the input x always equals that constant k. And law number 2, it must pass directly through the origin. That's the point 0, 0 on a graph. If it breaks either of these rules, bam, it's guilty of being non-proportional.
Let's move on to section 2. Tracking tables for evidence.
Now, what's really interesting about this slide is how we use our first tool in the field, the data table. Tables are just brilliant for uncovering hidden mathematical behavior. Just look at this babysitting data. You work 1 hour, you get $8. 2 hours, $16. 4 hours, $32. Let's test our first law by dividing the y column by the x column to find the ratio. Well, 8 divided by 1 is 8. 16 divided by 2 is 8. 32 divided by 4 is... you guessed it, 8. We have a perfect, unbroken constant ratio here. This $8 an hour rate passes the table test with flying colors.
But watch out, because mathematical crimes can happen right in plain sight. Take a look at this comic book pricing table. At first glance, buying 2 books for $6 gives us a ratio of 3. Pretty normal, right? But wait, look at the next row. 6 books cost $16. If we divide 16 by 6, we get a ratio of roughly 2.66. The constant ratio is totally broken. Even though that third row goes back to a ratio of 3, the damage is already done. Because the multiplier changed even once, this claim is undeniably non-proportional.
All right, section 3, the graphing test. So, tables are great, but sometimes we really need to visualize the scene of the crime using a coordinate plane. Graphing gives us a super simple, incredibly strict two-step visual test that every good detective needs to memorize. Step 1. When you plot your data points, do they form a perfectly straight line? A straight line shows a constant rate of change. But remember, actually listen closely to this. A straight line alone is not enough. You've got to proceed to step 2. Does that straight line pass directly through the origin, 0, 0? If it misses the origin, it fails the test. Period.
You might be wondering, why are we so obsessed with the origin? Well, because context really matters. In a real-world proportional relationship, 0 inputs absolutely must result in 0 outputs. Think back to our babysitting example. If you work 0 hours babysitting, you must earn exactly $0. You know, you don't magically start with $20 in your pocket just for showing up to watch TV, unfortunately. So that 0, 0 starting point, it's completely mandatory.
Moving right along to section 4, equations as hard proof.
Let's move to and see how this builds, because we've tracked tables and checked graphs, but now we need the absolute hard proof. We need to look at the mathematical DNA of our suspects, the equations. When you look at a proportional equation, its DNA is incredibly clean. It always takes the exact form, y equals k times x. For example, y equals 4x. There's no extra baggage there. But look at a non-proportional linear equation, like y equals mx plus b. An example would be y equals 2x plus 4. Do you see that extra plus 4 tacked on to the end? That's the y-intercept, and that little addition completely breaks our strict origin rule. Because when x is 0, y is going to be 4, not 0.
So here is a really quick detective checklist for spotting the fingerprints of non-proportional linear relationships. First, it has a starting value that is something other than 0. Second, you'll actually see addition or subtraction right there in the rule. And third, because of that addition or subtraction, the graph is guaranteed to cross the y-axis somewhere above or below 0. Basically, if you see these finger parts, you know for sure it's not proportional.
Section 5. Comparing competing claims.
All right, detectives, this is it. It's time for the ultimate showdown. We're going to test two competing claims back to back using all the evidence we've just gathered. Look closely at this side-by-side data. Claim A is tracking earnings from cups sold. Claim B is tracking the cost of our suspect taxi fare from the very beginning of our investigation. I want you to look at the inputs and the outputs here. Which one actually holds a true constant of proportionality? Which one passes through the origin? Let's check the 0 row. For 0 cups sold, you earn $0. Makes sense. But for 0 miles driven in the taxi, wait a second, it already costs $4?
And this brilliantly illustrates our point. The evidence literally doesn't lie. Claim A is purely proportional. The equation is y equals 4x. It passes through the origin, and it has a perfect constant multiplier of 4. But claim B, the taxi fare, it is totally guilty of being non-proportional. The equation is y equals 2x plus 4. That $4 base fare acts as a starting value, which entirely breaks the origin rule and completely ruins any chance of a constant ratio.
Now, as an investigator, finding the truth isn't quite enough. You actually have to be able to explain it to the jury. Here's a perfect example of a grade 7 evidence-based justification. The relationship is proportional because the ratio of y to x is constant and the graph is a straight line through the origin, 0, 0. Notice how it specifically cites the laws we discussed? That, my friends, is exactly how you write an airtight verdict.
Finally, Section 6, the final verdict.
As we wrap up our investigation today, we've seen that tables expose a broken ratio, graphs show a line missing the origin, and equations act as the ultimate DNA test. So I'm going to leave you with one final cliffhanger challenge for your brand new detective skills. Look at these two equations, y equals 6x and y equals 2x plus 7. Based on absolutely everything we covered in today's explainer, which one is guilty of breaking the laws of proportionality? Look at the evidence, trust your training, and decide for yourself.